in this session we would be discussing one of the important topics in climatology, that is temperature. Under this session we would be talking about insolation, heat transfer, lapse rate and various scales of temperature. We would be continuing with temperature inversion in the next lecture. Now let's first start with insolation. What is insolation and how do we measure it? That's the first question we will try to understand. Insolation, as the name suggests, it's derived from that is incoming solar radiations. So in means incoming. So whatever solar radiations are coming in, if I abbreviate it, we call it insolation. Now when we try to measure insolation, I can say it is the average irradiance which can be measured in watts per square meter per day. So I can say watt per square meter per day would be how we can measure insolation. Now this is a device which can be laid down onto a horizontal surface and can be connected, and this device would help you find out the insolation of the region. In this diagram, you can see you have the equatorial region and the polar region. So what is happening towards the equatorial region? The equatorial region receives direct sunlight. When there is direct sunlight that is received in a certain region, what would happen? It would be concentrated into a smaller area and it would have higher concentration. So this would have higher concentration and it would be limited to a smaller area. However, if we move on towards pole, what would happen is the same sunlight which is falling would appear to be slanting. So there would be slanting rays that would fall towards the polar regions. As a consequence, what would happen is the area in which the sunlight is falling would be much larger. Since the amount of area increases, the concentration of the sunlight would decrease. So I can say due to larger area, the amount of insolation would decrease. So this is the basic idea we try to understand to find out the reason behind insolation and the factors that affect insolation. But before we start with the factors that affect insolation, one of the most important thing is, I can say in very simple terms, it's the difference between the atmospheric, the solar constant and the atmospheric loss of the sun rays or the heat from the atmosphere, and that would be governed or that would be known as the insolation of the region. Now if I try to understand the factors that affect the insolation, I can say there are two basic factors that affect insolation. First is the solar constant and next is loss in solar irradiance. When I say solar constant, how do we understand solar constant? Solar constant is a measure of flux density, and when we try to say it's a measure of flux density, it means that the mean solar radiations per unit area that are falling into a region, that has to be determined. So it's the mean solar radiation that are falling into an area that has been demarcated at a distance of 1 angstronomical unit from the sun, and this 1 AU is the mean distance between earth and the sun. So this is the mean distance between the earth and the sun, and this governs the solar constant. Now insolation is primarily governed by these two factors. If I further classify solar constant, I can say three factors affect the solar constant and eventually the insolation or the amount of incoming radiations on the earth. First is the earth-sun distance. The earth-sun distance is an important feature because you have sun and this is the path of the earth. There is a point on the earth where, there is a point on the path of revolution where earth lies closest to the sun, and there is another point where earth lies at a maximum distance from the sun. The point where it is closest to sun is known as perihelion. Helion means heli means related to sun. So peri, the best way to remember is, in Hindi you can remember it as peri or pas. That means it is closest to the sun, and epihelion, which is farthest from the sun. So this region which is closest to the sun, which will receive maximum insolation at the time when sun is closest to the earth is closest to the sun, it will receive maximum insolation. At the time where it is farthest from the sun, it will receive minimum insolation. So that is one factor, that is earth sun distance. Next is solar variation. I can say there is a 11-year or 22-year cycle that operates, and the 11-year cycle is known as sunspots, and these sunspot activities affect the amount of insolation. Axis, shape and altitude. Now axis, we can say that earth is tilted at an axis of 23.5 degrees, and this tilt is responsible for the incoming solar radiations from the sun. So towards the equator you have direct radiations which are much higher in concentration as compared to the poles that we already saw in the last diagram. So axis, shape and altitude. Higher altitudes, as you move higher in the altitude, we will refer more when we will talk about the vertical and the horizontal distribution of temperature. There is changes in the temperature that occur. So temperature decreases as you go up in the troposphere, but that is limited to troposphere. We will see further how the temperature moves. So these three factors affect the solar constant. The next is loss in solar irradiation. It's affected by the length of the day. If the length of the day is more, the amount of incoming solar radiations would be more. The angle of incidence, if the angle of incidence is perpendicular, the amount of insolation would be much higher as compared to at an angle of 30 degrees or 45 degrees. Then transparency in the atmosphere. If there is clouds that are present, it would obstruct the insolation. However, if there is clear atmosphere, it would lead to more insolation that is coming up into the region. So these are some of the factors that affect insolation. Now when we talk about insolation, there is another two important thing that we must be clear of. First is the solar spectrum and the solar intensity. Solar intensity can be explained as I double the distance, the area covered becomes 4 times. So if this is the area covered at a certain distance from the sun, if I double this distance, the amount of area covered for insolation would become 4 times. We understand this more by the various laws that we would be discussing in a separate session. And then next is the solar spectrum. The solar spectrum explains that insolation is mostly in the form of short wave radiations. So short wave spectrum or short wave radiations largely affect the insolation of the region. So these two are another important thing that we need to be very clear when we talk about insolation. Now in this diagram, as you can see, you have the yellow line that denotes the equatorial region and the blue line that denotes the polar area. So as you can see, insolation in the equatorial region is more or less constant throughout the year. However, the insolation or the incoming solar radiation for poles is maximum for 6 months, and so we say 6 months day and 6 months night. So for 6 months night, you do not have any insolation that can be seen. You have insolation or the incoming radiations that are seen only for the 6 months, and that to peak up in the month of June and July. So that is how we understand the variations in the solar intensity or the solar insolation. Now the next important topic in temperature is heat transfer. Under heat transfer, we talk about 3 terms, that is radiation, conduction and convection. We will explain it by a very simple means of a teacher and a student in a classroom and students in the classroom. So what the teacher has to do is, teacher has a book and she needs this book to be transferred to the last candidate of the class. Now how can this be done? There can be 3 simple processes that can be applied. So first is, teacher will hand over the book to the first candidate, first to the second, second to the third, third to the fourth and fourth to the fifth. And that is the transfer of heat. In terms of heat, if we talk, that is transfer of heat by direct contact. So directly you are handling the book and one person is giving to the next, next to the next, and so on. So if I have a rod, a metal rod which is heated at this end, by conduction process it would slowly heat up till the end of the metallic rod. So that process of direct contact, I can say, would be known as conduction. That's the first process. Now the next process would be convection, where teacher hands over the book to the first candidate. The first candidate moves from his or her place and finally goes to the fifth candidate and hands over the book, and this process is known as convection. A simple way to understand is, let's consider a hot water boiling in a bowl. What would happen is, the lowermost molecule would become hot. As a result, they would rise up and the upper molecules will condense down. So this process is known as convection. And finally is the radiation. What teacher would do is, teacher will directly throw the book to the final candidate, that's the fifth candidate, and the fifth candidate will receive the book, and this process is known as radiation. And this radiation process is the process by which we receive sun rays onto the earth. So that process is known as radiation. So these three are the basic process of heat transfer that we must know when we are talking about heat transfer and insolation. Now next is the vertical and the horizontal distribution of temperature. When we talked about layers of atmosphere, we have already discussed how the temperature gradient changes from one layer of atmosphere to the next. However, we will repeat that again in brief. And then across the horizontal distribution, when we say, I can say the equatorial region you have hot temperature, and as you move towards the polar areas the temperature becomes cold, and that I can say is a very simple classification to explain the horizontal distribution of temperature. When I say vertical distribution of temperature, what would happen is, in the lower regions of the troposphere, what would happen? Due to the surface of the earth, the heating effect will take place from the ground, and that heating effect would lead to rise of the air parcel. As a result, there would be decline in the temperature in the initial section. This will continue to the region of tropopause. At tropopause, what would happen is, as soon as they would enter stratosphere, ozone would absorb the ultraviolet rays, and this absorption of ultraviolet rays would lead to further increase in the temperature. When there is the next section, that is mesosphere of the atmosphere that occurs, there would be no ozone to absorb the atmospheric ultraviolet rays, the UV rays. So what would happen? There would be further decline in the temperature, and finally towards the thermosphere and beyond, there would be ionization of the gas that would take place, and that would again lead to rise of temperature, and this rise of temperature would be steeper. So this is how atmospheric change in the temperature takes place when we talk about vertical distribution. Now the most important thing is understanding the lapse rate. Now when I talk about lapse rate, in simple terms I can say lapse rate is the rate of decline or the fall of temperature with height. So as we move higher, there is fall of temperature. Let's consider ourselves to be in the region of troposphere itself. Let's confine ourselves to this region first. We will be discussing how the inversion takes place in the next lesson. For now, we will confine to the layers of troposphere. What would happen here? You have the ground. This ground would act as a heat source, and you have an air parcel here. This air parcel would get heat from the ground. Consider this to be a idealized situation where the air parcel is maintained hydrostatically, and you have the only source of heat, that is ground. So I can say this air mass could be considered as a case of ideal gas, and it is thermally induced, or I could say it is a adiabatic process with no heat exchange that is taking place from the surrounding atmosphere. This heat, when this air parcel receives certain heat, what would happen? This air parcel will get energy. This energy would help to move the molecules faster. So movement of molecules would occur. This movement of molecules would lead to expansion. When there is expansion, what would happen? there would be fall in the density, and this decline in the density would lead to this air parcel rising higher. So this air parcel would start to rise higher into the atmosphere, and this will rise till the point it starts to receive relative humidity. As and when the relative humidity in this air parcel will increase, so you have rise of relative humidity. This rise of relative humidity will lead to a situation where you have dew point that would be reached, and the point where I can say there is dew point that is reached, there is latent heat of condensation that would be generated. So you have latent heat of condensation that would be generated, and at this point you would have formation of clouds. So in this diagram you can see you have the the air parcel that is rising up, and till the point there is no intake of no rise of relative humidity, or it is not reaching the dew point or the condensation level. We call this section as the dry adiabatic lapse rate. At the certain point where condensation is reached, you have latent heat of condensation that would be generated and cloud formations would take place. Beyond that, there would be decline in the fall of temperature with altitude. So actually, if there a fall of temperature should be 10 degrees Celsius, if there is saturation that has reached, the fall of the temperature might be 6 degrees. So you have decline of the temperature drop that takes place with altitude, and this region is known as moist adiabatic lapse rate or saturated adiabatic lapse rate. Moist adiabatic lapse rate or saturated adiabatic lapse rate varies from region to region. However, dry adiabatic lapse rate is more or less constant for most of the region. The fall of the dry adiabatic lapse rate is around 10 degrees Celsius per kilometer or per 1000 meters, I can say. However, fall of the adiabatic lapse rate is 6 degrees Celsius per kilometer or per 1000 meters, and it fluctuates or it varies depending on the region it is. Now, the another important phenomena is these two are the adiabatic lapse rate. Besides that, we have the environmental lapse rate, and that is the normal lapse rate or normal fall in temperature with height, and that is known as environmental lapse rate or atmospheric lapse rate in certain cases. Now, when we are understanding the concept of lapse rate, there is an important concept that is missed in most of the cases. We would be trying to touch that topic briefly here, and that is when we talk about the role of Tibetan Plateau. Now, role of Tibetan Plateau is indeed important for monsoonal activities, but what is the role when we talk about in terms of lapse rate? So, temperature of the lapse rate are much steeper in isolated mountains as compared to huge mountain ranges, because if I have a kind of steep mountain that is here, this would be a heat source, but I have another set of mountain or plateau here which is much extensive. So this would be much bigger heat source as compared to this mountain. Therefore, the role of Tibetan Plateau is very important, because Tibetan Plateau extends for nearly 2000 kilometers. In west it's around 600 kilometers, and here it has an extension around 1000 kilometers, and it's located at an elevation of nearly 4000 meters and above. So this huge landmass affects the lapse rate of the region. Usually this region, because it's such extensive, it acts as a heat source. So when I talk about the mountain lapse rate changes, there are two basic factors that affect the lapse rate in the mountain region. First, the mountain itself, which acts as a heat source, and second, the orographic induced cumulus cloud formations. So orographic, that's the mountain induced cloud formations, and these cloud formations are usually in the form of cumulus clouds. Okay, and this cloud formation is responsible for generation of latent heat of condensation, and finally affecting the lapse rate. So drop in the lapse rate as compared to the surrounding areas is much higher when it comes to the case of Tibetan Plateau, because Tibetan Plateau you have temperature which is around 1 to 6 degree higher as compared to the surrounding areas or the same areas which are at the same altitude at the sea level, above the sea level. So you have a much higher temperature in this case, and because of that you also see most of the I could say the highest timberline that exists, and this timberline is not at the Tibetan Plateau but at the southeast of Tibetan Plateau. The only reason being is the high heat source of the Tibetan Plateau here and the fall of the lapse rate. So with this we cover the section on temperature. We would be covering so this diagram again explains the dry adiabatic lapse rate, and at a certain level you have condensation that is reached, and beyond which you have the moist adiabatic lapse rate where the decline on the temperature is much less with altitude as it should have been in the case of dry adiabatic lapse rate. So with this we cover the concept of lapse rate. We would be covering the inversion of temperature in the next class. However, let's talk about the scales of temperature. The scales of temperature, we usually talk about the 4 basic scales: the Fahrenheit, degree Celsius, Rankine and Kelvin. Here are some of the conversion formulas that you can see. Now Fahrenheit is nearly obsolete in most of the nations except in US and Belize, where you have Fahrenheit that is used. Degree Celsius is the most common, where you have 0 degree, that's the freezing point, and 100 degrees, that's the boiling point. You have the equivalent of boiling point that can be seen here in different scales, and equivalent of freezing point that can be seen at different scales here, and this is the point where you have the absolute 0 for all the 4 scales. So this is a kind of brief introduction to the various scales that are used for measurement of temperature. In the next class we will talk about the temperature inversion, the basic idea and the various types of temperature inversion. In the further next class we will focus on the Tibetan Plateau and the latest developments in the field of Tibetan Plateau and its effect on Indian monsoon and the global changes that are occurring in the climate because of the changes in the structural formation of the Tibetan Plateau. You can subscribe to our channel for any further updates and leave any doubts as comment below the video. We will be more than happy to solve any and all doubts you have. Have a good day ahead.